Let me ask you a question that might just turn everything you know about AI deployment completely upside down. Does setting an AI's temperature to 0 actually guarantee the exact same answer every single time? Well, we all thought it did, right? I mean, in the industry, setting t equal to 0 is treated as the absolute gold standard for determinism. It's supposed to be the ultimate lock on a model's behavior. But what if I told you we've kind of been operating under a massive illusion? What if 0 doesn't actually mean 0?
Look, this isn't just some theoretical hunch. Recent studies, like this incredibly eye-opening 2025 paper by Attil and colleagues, have revealed a pretty shocking truth. They systematically evaluated multiple LLMs under these supposedly deterministic settings, and you know what they found? Massive accuracy variations. We're talking up to a 15% difference across runs using the exact same input. Even the raw text outputs just weren't identical. And other researchers like Yang and their team hit the nail on the head with the exact same findings in code generation benchmarks. So the reality here is undeniable. Deterministic temperature settings simply do not guarantee output consistency. No way.
Okay, let's really dive into this. Welcome to this explainer, where we're unpacking a genuinely groundbreaking April 2026 research paper by Alberto Messina and Stefano Scotta from RAI-CRTS. They've finally solved this mystery for us by introducing a brilliant new concept called background temperature. Today, we're going to break down exactly why our AI models are secretly rolling the dice in the background, and more importantly, how we can finally measure and control that chaos. So here's our roadmap for today. We'll start off with the zero temperature illusion, then uncover the sources of this hidden randomness. After that, we'll introduce background temperature, talk about how to actually measure it, look at some jaw-dropping pilot experiments, and wrap up with exactly why this matters so much.
Section 1. The zero temperature illusion. The myth of t equals 0.
To really get the problem, we first have to understand the expectation. Now, at t equals 0, an AI relies on something called greedy decoding. It's supposed to just look at the probabilities of the next possible tokens and definitively pick the one with the highest probability. It uses a straightforward mathematical function called argmax. You'd expect 100% identical outputs every single time. But the reality? We get divergent text, we get varying accuracy. Why does this happen? Well, in regions where multiple tokens have very similar probability mass, even the slightest, most microscopic shift in the system can actually flip that argmax decision. And once that single token flips, boom, the entire rest of the generated sequence spirals off into a completely different direction.
Section 2. Sources of hidden randomness. The plumbing problem.
So, if we set the software itself to be perfectly deterministic, what on earth is causing those microscopic shifts? Turns out we have to look away from the AI model entirely and look down into the actual physical infrastructure it runs on. The real culprits injecting noise into the system are purely computational. We're talking about varying batch sizes, meaning how many requests the GPU is handling at any given second. We're looking at kernel non-invariance, which basically means the fundamental math operations behave slightly differently depending on the batch shape. Then you've got floating point non-associativity. In extreme high-speed GPU math, A plus B plus C doesn't actually always equal C plus B plus A. It's crazy, but it's due to rounding errors at the decimal level. Add in reduction order effects and the sheer chaos of fluctuating server loads, and your perfectly deterministic AI is essentially sitting on top of a faulty furnace that is randomly injecting heat or noise into your probabilities.
Section 3. Introducing background temperature, a new metric for hidden noise.
Messina and Scotta realized we absolutely needed a way to quantify this faulty furnace. So they introduced a really crucial new definition, background temperature, or TBG. I want you to think of it exactly like the literal thermostat in your house. You might hard-code the digital thermostat on your wall to absolute 0, but if your house has drafty windows, a busted furnace, and a dozen people constantly walking in and out, the actual temperature you feel in that room is definitely not 0. TBG captures the expected equivalent temperature induced by that messy inference environment, the hardware, the concurrency, the floating point math, even when your software is officially set to a nominal t equals 0.
Section 4. How do we measure it? Catching the ghost in the machine.
Okay, so theory is great, but how do we actually catch this ghost in the machine? How do you measure the background temperature of a massive black box cloud model where you can't see the underlying code? Well, the researchers built a very clever empirical protocol. The core problem is we obviously don't have a perfectly deterministic ideal system to compare our noisy cloud models against. So they designed a workaround. They took System B, which is the remote cloud service being tested. They hit it with a massive set of prompts at t equals 0 over and over just to see how its outputs naturally vary and scatter. Then they set up System A, their anchor. This is a local model running on hyper-controlled, locked-down hardware with fixed batch sizes and fixed precision. It acts as our stable baseline. From there, they artificially raise the temperature on this anchor model until its output variations exactly match the chaotic variations coming from the cloud model at t=0.
To break that whole process down into 3 simple steps for you, first, test a highly stable local anchor model at varying known temperatures, say 0.01, 0.05, 0.1, and so on. Second, test the massive unknown cloud model strictly at t=0. Third, match up the statistical divergence. We are basically just asking, hey, how much artificial heat do I have to inject into my perfect local model to make it act as erratically as this cloud model acts at 0?
Now here's exactly what we're looking for in that anchor model. When you run it at a true t=0, you get a solid, single block. A perfect spike of certainty. Every single time you ask the question, you get the exact same answer, 100% match. But the moment we bump that anchor model up to a temperature of 0.2, the exact match fraction scatters. The answers start becoming unique, and the distribution spreads out. By mapping this spread at every single temperature increment, the researchers essentially created a catalog of heat signatures that they could then use to measure our unknown models.
Section 5. The pilot experiments. The lineup.
It is time to bring this theory into reality. The researchers put this to the test on a model called GPT-4.1-Nano via Microsoft Azure, setting it strictly to t=0. And guys, this was the absolute aha moment in the data. The scattering of answers from the cloud model at 0 perfectly, and I mean perfectly, aligned with their local anchor model small LM3 when it was running at a temperature of 0.05. By using statistical distance tracking, they literally proved that the chaotic background noise in that Azure cloud environment forces the model to operate at a background temperature of 0.05, completely overriding the user's setting of 0.
But actually, they didn't just stop there. To make sure this estimate was absolutely rock solid, they brought in a second reference anchor model, a llama model this time, and ran the entire comparison all over again. The llama model indicated a background temperature of 0.1 for that exact same cloud setup. So by averaging the findings from multiple local anchors, they were able to refine their final estimate. The true background temperature for GPT-4.1-Nano in that specific environment wasn't 0. It was 0.075.
All right, here is the real payoff moment. This is the full empirical lineup tested by the researchers across models from the major providers. Check this out. Claude's Sonnet 4, tested via Amazon Bedrock, actually achieved a perfect 0. Every single answer matched perfectly, which means its infrastructure is incredibly tightly controlled. Grok 3 Mini showed a slight background temperature of 0.015. Gemini 2.0 Flash came in at 0.065, and GPT 4.1 Nano showed the highest hidden randomness in this specific test at 0.075. Now, to be clear, this is not a critique of how smart these models are. It's a direct, measurable reflection of the stability of the server pipelines they're currently running on.
Section 6. Why this matters. Fixing the furnace. So now that we can finally measure this, what do we actually do about it? Well, the beauty of background temperature is that it takes this vague, hand-wavy complaint about weird model behavior and turns it into a hard, actionable engineering metric. To lower a system's TBG, engineering teams can implement targeted interventions. They can use batch and variant kernels for core operations like matrix multiplication, so the math doesn't magically change just because the server is under heavy load. They can enforce deterministic reductions and ensure consistent numeric precision. They can fix kernel configurations across different data shapes and strictly cap concurrency buckets. Basically, all these deeply technical infrastructure fixes serve to insulate the house to ensure that when a user asks for 0, the system actually delivers a true 0.
And the impact of adopting background temperature goes way beyond just debugging your code. It's absolutely crucial for ensuring transparency and trust, especially in regulated AI spaces. Think about it. If you're deploying an AI for medical diagnostics or heavy legal analysis, you have to prove it's consistent. TBG actually allows you to audit that consistency. Plus, it prevents highly misleading model comparisons in research. If Model A beats Model B on a benchmark by some tiny margin, but Model A's background temperature variation is larger than that margin of victory, well, you haven't actually made a better model, have you? You're literally just measuring infrastructure noise.
I want to leave you with a final thought to ponder today. We spend so much time endlessly debating the intelligence and the alignment of these AI models, but we completely ignore the chaotic physical infrastructure they're running on. As AI begins to handle higher and higher stakes decisions, from autonomous driving to algorithmic trading, how much hidden randomness in the plumbing are we actually willing to accept? Next time you set t = 0, just remember, the ghost in the machine might just have a mind of its own. Thanks so much for joining me on this explainer. I really hope this changes the way you look at AI deployment forever.